working at Merck in the Department of Chemical Engineering Research and Development for 2 years now. And in that time, I've been working on the development and scale-up for a process to generate duravirin, which is an investigational NNRTI inhibitor for the treatment of HIV. So in particular, I've been working on one side chain of the process, which includes the final chemical coupling to form the API, crystallize it, and isolate it. In these last 2 years of development, this step has presented us with quite a number of interesting challenges, and I look forward to sharing some of those with you today in a sort of case study. I would like to start by providing you with a definition for the titular theme of my presentation. So at Merck, we've defined process fingerprinting as a collection of the fundamental process knowledge, mechanisms, kinetics, thermodynamics, and statistics. So the idea is to establish a deep understanding of the process, relying on rich data and models, and then use this to assess the performance of a process across all scales. In this case, we're aspiring to apply this kind of methodology to the lab and pilot scale development of the duravirin process. So by using some of the principles of process fingerprinting, we've been able to interrogate the process and establish large and diverse data sets that we've been able to use to enable rapid optimization and characterization efforts. I'll go into some more detail later about the tools that we've used in this development work, but one of the primary themes is the reliance on the collection of kinetic data to understand the dynamics of the process, and this includes solid phase behavior as well as traditional reacting kinetics. So my objectives here today are to share this approach with you as it relates to some of the more interesting scenarios in the development of the duravirin alkylation reaction, and to highlight some of the critical advantages that collecting this type of data has offered us, not only in generating the data, but in demonstrating our understanding of it. So as it applies to demonstrating our understanding for scale-up, tech transfer, and the development of a robust process control strategy. So here are most of the many of the tools that we have used in this development work. As I've mentioned, one of the primary themes of the work was the collection of kinetic data, and so to that end, we have primarily used 2 tools. So first, we have made tremendous use of METTLER TOLEDO's easy samplers in coordination with reactions run in their EasyMax or OptiMax thermostat systems. So this has been a particularly reliable tool for us, even for the use with fragile streams, including slurries and supersaturated solutions. And we've been able to use this over a range of temperatures from, say, -20 to upwards of 80 degrees Celsius. It's been a really great tool. In a similar way, but at a much smaller scale, we've used a tool called the AmigoChem Workstation. And so this is a parallel reaction block that's equipped with a liquid handler capable of doing automated dosing and sampling. So unlike with the EasyMax, the AmigoChem allows us to operate at much smaller volumes, as low as 4 milliliters, or with special volume inserts as low as a 1/4 milliliter. For the purposes of this work, we ran our AmigoChem reactions at the scale of 10 milliliters, mostly to kind of decrease some of our sensitivities to charge accuracy and things like that. So obviously running in this kind of equipment at a low volume allows us to be very resource efficient. And running 10 reactions simultaneously with sampling allows us to churn out data-dense experiments to the point that analysis actually becomes the bottleneck. And so with respect to analysis, we use HPLC as the primary means of assessing the performance of this reaction. However, to enable faster processing times, we also relied heavily on UPLC, so reducing like a 30-minute method down to like 6 minutes or so. Nonetheless, using these kinds of tools to generate dozens or even hundreds of samples in a given week has its own separate burden. And so to meet that need for processing all these chromatograms appropriately, we've also used some customizable automatic integration parameters in Agilent ChemStation software, which has been really good for generating consistent high-quality integration for impurities as low as 0.05 or 0.1%, being able to track these things qualitatively without manual intervention, except for some spot checking here or there. So with process data in hand, one of the tools that we used, here's their logo, is a Design Expert. And so we've used this to build some statistical models, and I'll go into that a little bit more later. Traditionally, we use this in our department for the design and evaluation of statistically designed experiments, or DOEs. We've also used a program called Spotfire to streamline some of our visualizations of quite large data sets. So very much unlike plotting things in Excel, Spotfire allows us to change graphical data on the fly. So you're non-disruptively changing axes, transmitting the data, and even completely changing the graph type in kind of a comfortable interface. So last but not least, we've also used PVM and FBRM for the characterization of solids at times in our development, and I'll share these later. When we've used these, and this kind of sits on the border between kinetic data and solid and slurry characterization, because we've used it for, this is the React IR, we've used this for the characterization of slurries in so much as we've measured the in situ concentration of the dissolved phase. So again, I'll go into that more later. Okay, so here is an overview of the chemistry. In the final chemical transformation of the derivative process, this alkylation here, pyridone is our limiting substrate. And so we use this as the basis for all of our equivalents and volumetric charges of reagents and solvents. Operationally, though, we first generate this N-methyl CMT intermediate, and this comes from a through process via the chlorination of a similar molecule, HMT, using thionyl chloride. So unfortunately, this generates sulfur dioxide and HCl as some byproducts, and both of these affect the downstream alkylation reaction. To that end, we execute a vacuum degassing workup to remove the SO2 the best we can, although to low and variable, but still significant levels. Unfortunately, NMP is actually also used in other industries as an agent for the capture of SO2, and so it becomes a thermodynamically difficult problem. So at scale, for example, to remove the SO2 completely to insignificant levels where it wouldn't affect the reaction, that's a process that could take like a week. So at any rate, we charge the pyridone to the CMT solution, and we correct the concentration using an additional charge of NMP. We actually use TML alcohol as a co-solvent, and this is useful in modulating the selectivity of the reaction as well as modulating the kinetics of the subsequent crystallization. So the reaction begins with a controlled addition of an excess of dipya or Hünig's base followed by an age. And so we age this reaction until we determine completion by less than 1 LCAP of pyridone, our starting material, by HPLC. The reaction is then terminated with a quench of acetic acid. And so at end of reaction, we observe 3 primary process impurities, which are going to be important to the talk here. So one of which is the O-alkylation impurity, and that comes just simply from the alkylation of a tautomer of the starting material pyridone, which forms in solution. We also have a bis-alkylation impurity, which is the overreaction, and this forms through the sequential alkylation of our derivative and API with an additional molecule of CMT. Third, and most simply, the pyridone starting material is our final process impurity, which we can measure at significant levels when the conversion is not high. It's worth noting that pyridone and the CMT also come in with some of their own reactive intermediates, especially because the CMT is generated in a through process. And I'll touch on some of these later. Okay, so here are some compiled results that I would describe represents the majority of what I would call the process fingerprint for this reaction. So the design of this experiment, which you see in the METTLER Optimax here, was kind of simply just to load in as many tools as I had available to myself, and then to let the reaction run. So prior knowledge is useful in determining which of these tools might be the best to choose, but I would add that if prior knowledge had captured everything, we wouldn't really have a lot left to learn. It's difficult to say what you don't know until you know it, and a lot of the work that I'll share here, I think, supports that notion. We've discovered things that we didn't previously know, or that just outright contradict prior knowledge, so I'll share some of those with you. At any rate, to characterize the solids in a reaction that begins as a slurry, we used FBRM, and the total particle counts in millions are here in black. Because I know that I'm adding a base to an acidic stream, I figured it also might be valuable to add a pH probe. Now I understand that pH is not necessarily the most appropriate term to be characterizing this property of a system of strictly organics. But nonetheless, we see the expected kind of behavior here, and we get some good information out of it. So I've plotted the pH in quotes in orange here. In red and blue, then, we have the product and the starting material, which I'm tracing by FTIR, also using the React IR. So I've calibrated this against traditional LC samples, which I've pulled with an easy sampler. To my initial surprise, using the METTLER IC Quant software for this model calibration effort was really only like a 10-minute exercise. And in doing so, it grants this like nice, clean, continuous data. And this continuous data is useful in helping to kind of elucidate some of the intricacies that intermittent samples might have otherwise missed, and especially in this case with respect to the initial reaction rates. Of course, IR is also useful in identifying some reactive impurities that the LC might not pick up on, but this was not the case here. Dipya, our base, was added via automatic dosing pump, also connected, this is METTLER's dosing pump, also connected to the Optimax, and so we're able to track the equivalence of dipya added over time, and I've plotted that here in green. Lastly, I have also plotted the jacket temperature offset relative to a constant, well-controlled reactor temperature, and I'd say that surprisingly this affords its own richness in data. So if we walk along this, we first initially see this expected exothermic reaction from the addition of the base to the acidic stream. Slowly the pH begins to rise, and it eventually forms what you see here as this kind of like titration cliff. At the inflection point of this titration curve, then, we see that the pyridone solids begin to dissolve and the reaction proceeds. contrary to prior knowledge, about 25% of this reaction actually proceeded before the solids are fully dissolved. Fortunately, closer analysis of this effect and supported by further experiments tells us that this short reaction window luckily is not dissolution limited. So looking back at the temperature data, I would add that it's quite obvious to see where the reaction begins. And interestingly enough, because of the sensitive measurement of the jacket temperature, this alone sufficiently describes some of the other information for the start of a reaction. I would say that this is important because the amount of acid that we can bring from the previous through process can vary batch to batch. So we can use this temperature data alone in all the experiments that we run in this equipment to correlate back to the amount of dipya that goes into the quench, right, and the amount of dipya that's actually free for the reaction. So something that wouldn't be so obvious if it wasn't for this sensitive measurement. I would also add here, you can see these little blips of just under 0.1 degrees Celsius, and this is actually caused by the actuation of the easy sampler probe. So if you forget where you pulled samples, I've done it a couple times, go back and find them. So some of our initial work involved screening through the many process variables of this reaction. I used the AmugaChem. I ran combinations of these variables in parallel reaction sets, like screens. And so some of the responses of interest, for example, would be the reaction rate of the pyridone starting material, or the overreaction rate for the bisalkylation, the overreaction impurity, or just the rate of generation of other impurities. Another response of interest is the selectivity of the O-alkylation impurity to the N-alkylated API product. Some of the inputs, for example, would be temperature, the NMP and TMO alcohol solvent ratios, the starting concentration of the pyridone CMT starting materials, and some charge rates, base equivalents, and the SO2 concentration. So I would say that the visualization here is actually a little bit oversimplified. So we didn't just run reactions in sets of, say, A, B, high and low, but I would describe it instead as like a quasi-model-based approach, which we use to help elucidate between potential models and mechanisms. And in doing so, we're able to deconvolute some of the more complicated relationships between the variables that we have in this system. So for example, deconvoluting between the effects of solubility, concentration, and selectivity that are invoked by this two-solvent system. Another area of interest was the formation of the bisalkylation impurity. And because of some of this data, we now believe that, at least in some part, this impurity is formed by the dimerization of the CMT starting material and not just because of sequential alkylation. So the CMT starting material, so we can go back, in the presence of dipya, for example, can actually alkylate itself on the amine here. And then that dimer molecule goes to alkylate pyridone directly to the bisalkylation rather than through the sequential alkylation. So after several cycles of parallel reaction sets then, the data was pretty sturdy. So we had collected, at this point, about 60 reactions with 600 samples or so, each combination of 5 to 10 reactions with 10 samples each, only really requiring about like 3 hours of active hands-on work. At this point, we're able to definitively understand all the relationships between our various inputs and outputs. And so I've defined the various reaction rates and selectivities as you see here. Through a detailed analysis then of every impurity in the reaction as well, we're able to determine that most of the starting material impurities react to completion as a function of conversion. For any impurities which we've identified which increase or decrease otherwise over time, we flag these and evaluated them in later studies. So unfortunately, I'm not talking about that today. So some of the relationships were quite straightforward, and they're able to be explained by simple empirical expressions. And for example, the selectivity to the O-alkylation we can actually describe based on a linear combination of the effects of temperature and co-solvent composition. Other more complicated effects, on the other hand, we sought out to use modeling tools and DynoChem to explain. Initially, this gave us some challenges where there were gaps missing in the parameter space, and this informed reactions that we could go run and then feed the model. So unfortunately, after we were able to build a relatively robust model to meet our data, some pressing process needs redirected the development efforts. So here we go. So based on some early process knowledge that we had about the subsequent crystallization, we knew that this O-alkylation impurity of interest was subject to a hydrolysis reaction to form our pyridone starting material, so regenerating the starting material in conditions of the crystallization which are high temperature and it's water rich. So unfortunately, what we find in some early characterization work is that both of these impurities exist above their solubilities in the final product slurry. And so what this means is that at some point we might crystallize out these impurities to failing levels. And of course, this was the case in some extreme situations we found in the lab. So it's at this point that the team recognized kind of a fundamental design principle to not fight thermodynamics with kinetics, because eventually thermodynamics is going to win. And so it was almost easy to say, like, this has never happened at scale, or these are only such extreme cases where we're observing this effect. But as we know, there are so many things that can affect the metastable zone width, including some things that might change at scale, including like a batch-to-batch variability of impurities, or shear, for example. So kind of not relying then on the kinetic control to purge these two impurities, we look back. We could simply solve this problem then by pulling back on some of the anti-solvent and diluting our crystallization. Of course, that takes back from our API yield doing either of those things. And unfortunately, because of the high load that we had here and this serious problem where these impurities were between 30 and 100% over their solubility, those kinds of changes would require too big of a hit to the API yield. So we looked back and we first said it would be better to optimize the reaction, reduce the impurity load to an absolute minimum, and then at that point we can revisit any parameters that we'd like to change in our crystallization. So luckily the rich data set, especially with respect to kinetics that we had for the reaction that I've described, helped us do this optimization quickly. Of course, it gets more complicated. So in what was really like an accidental discovery, I ran an alkylation reaction at high temperature, intending to make a stream rich in alkylation that I could then use to enrich, isolate, and then use that for solubility studies to address this problem we're having with our crystallization. So I figured, based on our previous knowledge, running at high temperature and in an NMP-rich system, we would be able to do this. And so you see, it starts to go up higher than we've ever seen at 8 versus like a typical level of like 4 LCAP. Of course, what we end up with then, as you can see here, is lower levels than we've ever observed. And so this was pretty interesting. Not entirely surprising because we know that there's a hydrolysis reaction which regenerates our pyridone starting material. But somewhat surprisingly, and I haven't shown it here, the starting material pyridone never increases over the course of this change. And so what we can hypothesize at that point is that either the consumption rate of the regenerated pyridone is significantly higher than the hydrolysis rate, which regenerates it, or perhaps it's not hydrolysis at all. And so we ran our set of reactions to kind of interrogate this effect. And what we found is that there's really no sensitivity to the water for this hydrolysis reaction. And in fact, this 0.06 weight percent, on which we see almost complete conversion, is far less than equimolar required to drive that conversion. And so instead, what we've identified is a base-sensitive isomerization of our highest impurity back to our API. So this is potentially a huge deal for us. So we've regained 4% yield, like a 95 to now 99% pure process, and we've completely eliminated most of our impurities. So on the other hand, running at a higher temperature, this is at 70 degrees with respect to a 20C initial reaction, we have a huge sensitivity to our overreaction impurity, and so I'll go into describing that. At this point, we can take a stab at using the sum of our process knowledge to propose two options to move forward with for the process, right? So in either case, we say it would be ideal first to maximize the amount of conversion that we can get and minimize the impurity load. And so by running at cold temperatures less than 0 degrees, we find that we can achieve this target. And so you see this here in either early phase of both reactions. Unfortunately, what happens is that the reaction rate slows as we become limited by solubility effects, and the concentrations of all the reagents involved are quite low. At any rate, on the left here, we can leverage our newly found mechanism. We can then heat the reaction mixture up to 70 degrees and facilitate the isomerization of the alkylation impurity to regenerate the API. So the pyridone here is not really of interest, and it quickly gets consumed. On the other hand, we have to balance this isomerization rate in hand with the overreaction rate to form the bis alkylation. And so we have a competition here, and we decide at some point, based on our process design, that we want to quench this when we've reached our target impurity profile. On the other hand, we can warm up simply to near ambient temperatures. And in this case, we're left with high levels of O-alkylation because we're not isomerizing it, but we have much smaller levels of bis alkylation. And so the competition here, as opposed to here, is now between the pyridone consumption and the overreaction formation. I'll note that the level of alkylation we've been able to achieve in this reaction, for example, is much less than we had in the original design, such that we can still tolerate this impurity profile with just minor changes to the crystallization. In either case, I think it's quite interesting that by applying this two-temperature approach, we're able to almost completely deconvolute the two problems of this reaction. So in the first half of the reaction, we handle the challenge of the selectivity optimization. And so we've run cold. We find that we achieve about 80% of the conversion at this point, such that by the time we get to the second temperature, the poor selectivities that we would normally observe there are hardly influential because there's very little conversion left to go. It's also worth noting that while we do see some minor increase in the bis alkylation in the initial phase, it's only about 0.05, 0.06 LCAP, and there's really no appreciable growth until we reach the second temperature range. So almost completely deconvoluting two separate challenges, the optimization of selectivity and the optimization of reaction rates, by taking this kind of two-temperature approach. All right. So because we're able to regain a lot of yield and reduce our impurity profile, we figured it would be worth investing some time into characterization, some proof of concept for this first process, the hot process, I'll call it. Right, so to reiterate, this is run initially cold. We achieve the majority of our conversion. We have minimal impurities at that point. Then we ramp to a higher temperature, and we isomerize the alkylation to regain API yield and drive conversion. As I've mentioned, we have extreme sensitivity at this point, or overreaction. So we'll discuss that a little bit later. After being able to reproduce our initial results and execute some initial range finding to evaluate our new sensitivities and the robustness of this process, I ran a rapid 2 to the 5 minus 1 half-fractional factorial design using the AmigoChem. So 20 reactions, 200 samples, and from setup to analysis, this only took about 72 hours, most of which was age time. So in fact, it's only about 5 hours of active hands-on work to collect this whole data. So looking at the LC profiles for the reactions that we've run, we're able to use this to create statistical models that we then apply to understand our sensitivities. What we find is that, as I mentioned, for the bis alkylation impurity, we're particularly sensitive to CMT and SO2 concentrations. And so we have two scenarios. In one case, we have to charge a certain amount of CMT to be able to fully convert our pyridone, right? If we charge less than that, we observe much higher levels of pyridone. There's just some minimum we need for the reaction to complete. Now, on the other hand, if we charge too much CMT, we have this sensitivity to the overreaction impurity, which is dependent on the concentration of SO2. Now, of course, what we had done for our early characterization work, we used a stock stream, which had a higher concentration of SO2. And we find there that the process is, in fact, moderately robust. What we didn't see at the time until we did this kind of analysis then is that at lower concentrations of SO2, it's not robust at all. If we were to scale up this process, we'd have about plus or minus 2 kilos of charge tolerance between these two failure scenarios out of a total charge of about 900 kilos. So this analysis tells us we can't move forward with this process. We can't demand that kind of control over the concentration of SO2, say above a certain level but below another. And we can't demand drop-wise accuracy for our charges on the commercial scale. At any rate, all of this work took only about 2 to 3 weeks using the benchtop automation. And so with a huge amount of data generated in just 2 days, we're able to drive to the decision to reject a higher purity process that regains 4% yield based on this kind of unique understanding of the process through the use of statistical models applied in a sensitivity analysis. So moving forward then with our newly desirable cold process, we are left to optimize some of the parameters. And so I've shown here temperature. So it's very similar to the previous reaction. We initially run cold. We get most of our conversion, and we minimize the side reaction and the overreaction. And at that point, we warm to drive conversion and balance the overreaction. So with the objectives in mind to minimize the overall impurities and maximize the rate of reaction within the constraints of cycle time, stability, and our capacity for impurity purge, which I've detailed here, we go out to find these optimums. So again, a lot of this work was using the AmigoChem or the Easy Sampler. So quite simply, for the first temperature of the reaction, we find that we can get the best selectivity if we run very cold or very concentrated and high in co-solvent composition relative to our co-solvent TML alcohol. We do so until we find kind of a cliff for solubility, which exists just after minus 15 degrees. Now, beyond that point, the reaction behaves wildly differently because most of the pyridone is out of solution. So we picked minus 15 degrees, or minus 10 degrees for our target for the first temperature. I've defined stability here for the second temperature as the time between reaching the end of reaction for pyridone at 1 LCAP and the time that it takes between that and reaching an excessive amount of the overreaction, which we find at 0.4 LCAP. So analyzing this array of data that we've collected, we eventually determined that we were looking for about 24 hours of stability, and this is determined in our tech transfer to a pilot site. So we're looking for time between when we've reached the overreaction and then when we have to quench it. And that's because of some operational challenges that they might have with quenching or shift change or something like that. So we set out to find 24 hours. We're able to do so using this data. We went through a few iterations of what do we want for stability, and because we had it all at once, this was very easy to kind of go through this. So we picked 15 degrees. We can understand very well the sensitivity that we have to the temperature there. We know what it's going to look like if we are at 20. We know what it's going to look like if we're at 10. Unfortunately, at this point, we're running cold and concentrated during initial reaction. And so what we're left with is a slurry-to-slurry reaction. So I'd say ordinarily, this would be a concerning problem. So what we set out to do initially was to collect some solubility data. And this is an interesting problem because for our pyridone substrate, initially, it is I would say it's almost impossible to collect this traditional solubility data appropriately because it is both pH and matrix sensitive. Now, if we take the reaction matrix and we expose that to the appropriate pH, of course, the reaction proceeds and our substrate gets consumed. So looking for traditional solubility data in that way wasn't going to work. So instead what I've done is I've used the React IR and I've obtained in situ concentration during the reaction, calibrated against manual samples filtered and assayed for the supernatant concentration. And so again, I've fit that model to the IR data, and I've plotted some of the data here. The total slurry was quantified, on the other hand, just using traditional LC with the easy sampler. So I've overlaid both of those here. What we find is that initially, we only have about 30% of our starting material dissolved and available for reaction. As we add our dipia, this decreases to about 15%. So there's the pH-sensitive solubility there. So while the solid fraction of our starting material is reducing from about 70% to, say, 15%, the API begins to form, and it quickly nucleates and crystallizes out as its solubility is exceeded at 0.6 reaction equivalents. And so I'll note that this axis is just relative to the reaction moles, so we can kind of understand the relationship together. So we are able to validate some of these observations with FBRM and PVM, although I've not shown it here. It's a little bit difficult to see, but with PVM we can observe that the fine starting material solution, or fine starting material slurry, gives way to a coarse product slurry, which is distinctly distinguishable. Now, while this experiment on its own doesn't fully characterize the system and the risks of this slurry-to-slurry reaction, I would say that it's helpful in framing the problem. So we can understand that we're not crystallizing out API while the concentration of pyridone is quite high, for example, or that at the end of this phase, the total amount of pyridone is not very far away from its solubility. And so we can use this understanding of the mechanisms that are relevant to probe the appropriate follow-up experiments. For example, running the fastest reaction with the conditions of lowest solubility. And in fact, running those conditions across various scales, we never observe any effects of, say, entraining the starting material in your API. Further, to mitigate against the risk of potentially trapping your starting material in a crystal of your API, which is coming out, we've heated up to a second temperature after this. So we've heated up to a second temperature, and we've actually included a flush with pure NMP, such that we're sure that we have full solubility of both our pyridone starting material and our API product. So in that way, if we were to trap in any of our starting material into our product slurry, we're fully homogeneous, and we have a second age there, so we can alleviate any of the effects that might arise from that. So I'll just note that at the end of this development, we were able to scale this up from the laboratory scale to like the 2 kilo scale, about 30 liters, in a prep lab that we have at Merck. And fortunately, the performance of that larger scale reaction matched very well with all of our laboratory development at scales all the way down to a ½ gram. So in the latest piloting campaign, additionally, we found some inspiring success at a scale above 150 kilos, matching perfectly well despite these kinds of phenomena. So the last piece of my development work, which I'm interested in sharing with you today, is this development of this empirical correlation. So as I've described before, we have a sensitivity to SO2. And so if we plot the reaction progress as a function of SO2 concentration, we find almost a linear effect. And this inflection here is just due to the two temperatures. So we heat up and it speeds up. So because it's almost quite linear, we identify an opportunity here. So we hypothesize at first that the SO2 is inhibiting this reaction in so much as it's consuming our starting material CMT. And so maybe it's a stoichiometric kind of inhibition thing. What we find is that when we investigate this, our hypothesis is mostly true. And so we do have a very linear relationship between the molar concentration of SO2 and the molar conversion of our reaction. Unfortunately, what we find is that it is not stoichiometric. It's like 0.66 moles of SO2 to 1 mole of CMT. Obviously, if we take a variable CMT and SO2 concentration and we feed it into a fixed CMT equivalence, our reaction kinetics grant us, as you've seen, variable purity and rate. But if we fully characterize this system, we understand the relationships, we can use those in a feed-forward control and try and correct in advance for the anticipated effects of the system. And so that's what we've done. We found a linear relationship between the SO2 equivalents and our CMT equivalents, which we suppose it's consuming. What makes this more complicated, unfortunately, is that these two are interrelated. So the SO2 is actually contained in the CMT stream. So if we're to add more CMT to account for the SO2, which is consuming it, this actually brings with it more SO2. So SO2 is dependent on CMT, CMT is dependent on SO2, and the result here is this nonlinear equation. So C1 you can think of as the equivalence relative to our starting material alone. And so this we've optimized in different studies. The C2 then is just this molar relationship, which we've converted to some useful forms that we already measure at scale. So the SO2 concentration in mg per mil and the CMT in weight percent. And so this is the equation that we're able to come up with. And so if we fix in then a calculated CMT equivalence to handle our variable income, we end up with a consistent result. And so here's the demonstration of that. So if we take the same exact system that we've shown before, where this uncorrected situation, we find is, as we desired, we've completely reduced the dependence on the reaction conversion to this SO2 concentration. Similarly, we've almost normalized the kinetics for our starting material reaction and our overreaction, such that if you compare these two, at the time point of interest of 15 hours, which is where we typically call our end of reaction, we have a 900% decrease in the variability of our starting material and about a 350% decrease in the variability of our overreaction material. So this was not something that was easy to introduce into the tech transfer process, I'm sure, as you can imagine, but I'm very grateful for an innovative team that worked really hard to defend this approach, unfamiliar as it was. So here are some unique highlights that I've drawn out for the use of time series data. And in the bottom right, we look at the choice of diluent for a reaction. Initially, in some historic work for this reaction, we found the overreaction impurity being measured at, say, 1 or 2 LCAP and then decreasing to 0.2 over the course of the reaction. Of course, for an overreaction impurity, this does not make any physical sense. And so his first hypothesis it had to do with water. Water was initially introduced to reduce some peak splitting issues. But eventually, this kinetic analysis gave way to change the analytical method in order to measure something that's more relevant to this process. The other 3 data series here, collected by my colleague Brian Wyvrat, I'll walk through very briefly. So these 2 reactions up here were part of a range setting in some of our final PAR setting efforts. So what we see here, interestingly, is that the bis alkylation profile intersects itself 3 times. And so this is a result of the concentration and temperature effects of this 2-temperature reaction we have. Over here, we use this data to leverage the ability to cool down a reaction and get some more stability between the end of reaction and quench. Here we demonstrate the non-impact of using a kicker charge of CMT. So if we weren't able to get the right amount of CMT in there initially, we can charge in a little bit more, and there's really no relative effect. I would argue that for all of these, you're going to have a really hard time picking out one of these data points a priori to understand the way that these things work and the way that the reaction is operating. Now, maybe for some of these, you could pick out a single time point of interest that would help you figure out what's going on. But I would say that for the one on the top left particularly, there's not a single time point that you can pick which you're appropriately analyzing the differences between these reactions. So, just some unique highlights to the use of profile data and some of the advantages it's given us. So in summary, we've applied some data-rich tools and benchtop automation to evaluate parameters and investigate some process mechanisms. In response to changing project needs, we were able to use this then to propose some redesigns and execute some rapid optimization studies. And then because of our kinetic understanding of some of the parameters, then we're able to propose this feed-forward correlation that I've described to reduce the sensitivity to SO2. The final result then is this really non-traditional slurry-to-slurry reaction where we have 2 temperatures and we rely heavily on this empirical correlation for one of our fundamental charge calculations. So, at any rate, what we're left with is improved yield, we've reduced our impurity load, and we've prevented the kinetic rejection of impurities, which I've described, and we've increased the stability. So these kinds of kinetic analysis and the data that I've collected here has allowed us to do this despite some of the more uncomfortable results in our final designed reaction. I'd like to thank all of the Duraverin team members in chemical engineering R&D, as well as our colleagues in process chemistry and analytical research and development. And I'd like to thank various members of the CERD Tech Labs, many of which were here, for helping me use these tools and dig into some of the experiments which I've run. And thanks to everybody at METTLER TOLEDO for having me here today to speak to you. Thank you.